So we're starting off with a discussion of motion. And I should have had you do this yesterday or right after your test. But it's sort of a what do you know. It's just, okay, let's toss everything on the table that you already know about moving objects. So tell me everything you know about moving objects. And most of you said something like, something causes them to move, or you referenced one of Newton's laws. Once they're in motion, they tend to stay in motion. A lot of you talked about kinetic energy. They are moving at some speed or velocity. Motion of moving objects is relative according to different perspectives. That's absolutely true. They have kinetic energy. It depends on what they're relative to. And what it looks like depends on where you are. They are they're moving based on a reference point. We see them in 3 dimensions. Oh, and some of this stuff comes up from yesterday. Had we done it before yesterday, some of those might not have appeared. Okay. And their subject, I don't have to refresh. It comes up automatically. They're subject to forces, and somebody mentions inertia, friction, momentum, acceleration, and we have to have a reference point to figure out the changes in their motion. Okay, so everything you know about measuring movement, and this is what we had started to do yesterday, and yesterday we hit this basic equation. Your average velocity is how far you get and how long it takes you to get, divided by how long it takes you to get there. Typically given in meters per second equals meters divided by seconds. That works dimensionally. And a few of you mentioned that you would measure distance. You would measure velocity. You could measure acceleration. You know what I don't see here in any of them? Okay, I have one. Okay. You can measure time. You can measure starting point and ending point. Okay. Time is really important in all the stuff that we're going to do. So we always reference velocity. We reference changes in velocity. We think a lot about distance, how far something moved, what its displacement is. But time's going to be real important for us in looking at motion. So a lot of you have a lot of the basic dimensions down. What's going to happen in the next couple weeks is you're going to turn moving objects inside out, and you're going to be able to determine anything about their motion. And I have not yet figured out where to tape the learning goals in this classroom. I have yours for this next couple of weeks. They also print them 2-sided. So in the next couple of weeks, you're going to be able to calculate any variable that affects an object's motion using the basic motion equations. Now, notice that equations is plural. You only have one on that note card so far. You're going to end up with 4 basic, 6. 4 what we call the basic kinematic equations, and then the 2 simplest ones like the one you got there. Okay, the other thing you're going to be able to do is accurately interpret graphs of objects in motion and make graphs representing objects in motion. You already have a good start on that from your lab. So you already know some things about representing objects in motion. Okay, which way do I have to do this? Like this. We will not start talking about falling probably for a week and a half. So right now, remember, we're talking about motion in 1 dimension, and we're only going to deal with flat surfaces for now. We're only going to deal with the x dimension of motion right now. Then we'll turn that on its head, literally. So let's get back to the notes and problems. Did anybody have any questions on the problems from yesterday? They're pretty simple 3-part algebra. Good? Okay. Velocity versus speed. So let me ask you this. If I tell you that something is moving at 38 meters per second, Is that a vector or a scalar quantity? Scalar. No direction. If I tell you it's moving at 38 meters per second north, that's a vector. So if I tell you it's moving at 38 meters per second, is that velocity? Well, no, it's just speed. It's the magnitude of the velocity is the speed. So if you give or are given a speed, it's just absent any directional orientation. Okay, graphical interpretations of velocity. This is pretty important stuff, and you started this yesterday. You can get velocity on your graphs from the lab. Time is always, of course, our independent variable. So we have time in seconds on the x. We have usually position on the y, and that's, in your case, it was given in centimeters. It could be given in meters. So for something that is doing this, tell me what that object is doing. So this is your position. 1, 2, 3, 4. This is your time. So first of all, let's answer this question. Is this object moving or standing still? Tarek? It's moving. Is it moving at a constant velocity? Yes. How do you know that? Okay, because the line is straight. The line is a straight line. That means what about this line is constant? Its slope. So the slope of a position time graph gives you what? Gives you velocity. And if you look at average velocity is equal to the change in position over the change in time. Hey, look at that. Slope equals delta y over delta x. It is the equation for average velocity. So let's play with this a little bit more. What happened to this object? What did it do? It stopped moving. So it moves for a while, it stops moving. What about this object? Okay. So we want to look at this from a couple different points on the line. So we can look at here to here. It's moving. Is its velocity changing? Yes. It's decreasing. The slope of the line is getting smaller. So we get to a point here where the slope of the line is what? 0. So the velocity, therefore, is 0. Now in, let's say, this section, what's happening to the slope of the line? What's happening to the slope of the line? It's increasing. Yeah, the slope of the line is increasing. So the velocity is increasing. So yeah, we have something that's speeding up, or it's here it's going pretty rapidly, starts to slow down, comes to a stop, and then takes off and is speeding up. So this could be somebody coming to a stop sign, sitting at the stop sign for a moment, and then hitting the gas. Okay? Let's do one more. Time in seconds. Position, we'll put this one in meters. And let's have two different objects here. So I have this object, we'll call it object A. And I have this object, object B. Write down for yourself. Compare the motion of these two objects. So jot this in your notes. What can you say about the motion of these two objects? Okay, what do you know about these two? So give me one point of comparison. Okay, B has a higher velocity than A. How can you tell?
Because the slope is greater.
Yeah, the slope is greater on B than on A. Anything else? Sarah? They're both moving at a constant rate. Yeah, the velocity is constant for both of them. Anything else? Yes, ma'am.
B is farther ahead than A.
Okay, in terms of their absolute position at the end of some time period, if we look at a time x, B is farther ahead than A. It's gotten farther than A. Its position is farther down the line. That pretty much covers it. All right, now, so we have an object that is doing what? It's accelerating. It's changing its velocity, and it's starting off slow, and it's picking up, its speed is increasing, the magnitude of its velocity is increasing. Those of you in calculus haven't gotten to this yet, but no, never mind, because you haven't gotten there yet, so we're not muddying the water. Okay. Can you find the slope of a line section like that with that curve in it? Does it have one slope from point A, from line A to line B? Is there a consistent slope there? No. The slope changes. So can we get an average velocity for that section? Not with the tools we've got currently, but it is possible to take an individual point on that line and draw what's called a tangent line. And that's a bad illustration of a tangent line, but let's see, it doesn't expand it on your screen. Okay. We can draw on any curve, we can draw a tangent line, which is a line that just intersects the curve at a single point. The slope of that tangent line is the slope of that individual point. Now, we don't do that a whole lot in here. The slope of that individual tiny little point is the instantaneous velocity. It's the velocity at that instant. When you hit the accelerator coming off a stoplight, your velocity is changing every millisecond. You're gaining velocity, you're accelerating. At every second you have an instantaneous velocity. That's what your speedometer shows. It's the velocity of the object at that moment. It can be pretty darn different than the average. So if we took these 2 points and we drew a line between them, we can get an average velocity for that section. And at some points the average velocity will be greater than at some points the average velocity will be greater than the instantaneous. At some it will be less. It's just going to be different. There might even be a point, maybe in here there's a point where they're equal for a moment. Okay? And this kind of sums up what we've been talking about. If it's got changing velocity, and you kind of know this intuitively, the line on a position time graph is going to be a curve. It's not going to be a straight line, and you get that. You can get it for a section. You can get an average velocity. It's not the same as the velocity at any given moment usually. We just do a tangent line. And like I said, we don't generally do that in here. In calculus, when you get to the point of differentiation, taking the first derivative gives you the slope of a point. But that's okay. You're not there yet. It's so fun, though. It's so much fun. Okay, so we could get, for instance, an average from there to there. And you can look at any point on that line and see if the slope of your average line is greater or lesser than the slope of your curve. So you already know this, and you know this from physical science, and you talked about it on your what do you knows. Acceleration is how fast your velocity changes. So it's how long it takes you to change your velocity. We talk about this a lot in car ads. 0 to 60 in I had a VW Rabbit diesel. 0 to 60 in just under 15 minutes. I love that car. So the acceleration, and again, my formatting got all screwed up. This is average acceleration. Is the change in velocity over how long it takes you to do it. Let's put that there. Now, so that's another one that really needs to go on your note card. That your acceleration is equal to your change in velocity over your change in time. Now, what's interesting, and you may or may not want to put it on your note card, and it's just a simple statement of mathematical truth. The average acceleration is also equal to your final velocity minus your initial velocity divided by your final time minus your initial time. You know, the interval of time in which the change occurs. So whether it's 0 to 30 meters per second, whether it's for a section of motion. So maybe we're interested in the time when you go from, maybe you're stopping or slowing down, the time when you go from 20 meters per second to 60, or you go from 60 to 20. Okay. Note, let's do a few problems with this. A couple things to notice about acceleration. It is a vector. It has a direction as well as a magnitude. And it can also be negative or positive. There's a word that I want to caution you about in a physics sense.
Deceleration.
Yes. So, colloquially, when I'll talk about decelerating my car on the road, but in truth, deceleration is kind of like a made-up thing. We're going to get into all the weird cases with sign and acceleration. You have negative acceleration, you have positive acceleration. You have slowing down, you have speeding up. So you have the magnitude of your velocity increasing or the magnitude of your velocity decreasing. But be careful, don't use the term acceleration in a physics sense, or deceleration rather. So if I have a position time graph, the slope of the line is the velocity. What if I were to graph velocity on the y? Now the slope of my line, because if you think about it, so remember, slope equals the change in y over the change in x. And acceleration equals the change in velocity over the change in time. The slope of a velocity time graph is your acceleration. And this is the very thing we say in the next slide. When you graph velocity against time, what you get as a slope is acceleration. It's the slope of the line on a velocity time graph. So let's play with some stuff here, shall we? What is that object doing? Accelerating. So tell me about its velocity. What's happening to its velocity? It's increasing. Is it increasing at a constant rate or a changing rate? Constant rate. Good. Now tell me about this object. It's not stopped. Yes. This is you on the highway on cruise control. Well, actually, your cruise control is not that perfect. You on the highway on cruise control probably looks a little bit more like this. There will be some little hills and valleys. Be really careful, because on a position time graph, that flat line is an object that's not moving. On a velocity time graph, that flat line is something that's moving at constant velocity. Constant increase, yeah. Okay, so don't yell this out. I want you to write this down on your notes. Come up with a scenario for what this object is doing. So you can put it in terms of a car. That's fine. You can put it in terms of a vehicle. That's one we're all familiar with. So give me a scenario for what is happening with this object. That was my thought. So you have a vehicle that is accelerating here. It's speeding up. Its rate of speed is increasing. Then it drives at a constant rate for a period of time. And then, yeah, my thought is like, I just saw a state trooper. Oops. I'm a few over. And, so they slow down, and then they're at another constant rate of speed. Now, we don't know what the velocities are. This could be, 3 miles an hour. This could be, me on a skateboard. No, that's not going to happen. But yeah, so you see, you can think about scenarios that would apply to an object that's moving. Let's practice one more. We'll have to record that. Okay, so the blue car has got a much higher rate of acceleration, much more rapid acceleration, much more rapid coming to a stop. Notice that I didn't say deceleration. The green car has a much more constant slope. Yeah, nearly constant, very gradual, very slow acceleration. It's in green because, of course, that's where you get your best fuel economy. Don't jackrabbit on the gas and brake. You get much better fuel economy if you drive gradually. It's true. We'll talk about it with force and stuff. Okay. So you guys are pretty good at this. Now let's add a wrinkle. Look at the blue car. I'm going to put some A, B, C, D. For which line segments is the acceleration positive? For which line segments is the acceleration negative? Jot it down. Who wants to take a crack at it? Tomas, I haven't heard from you all day. Where is it positive? You give me where is the acceleration positive? A to B. Okay, and I think everybody probably agrees with that. Where is the acceleration negative? Zach, you want to take that one? C to D, right, because the slope of the line is negative. Where's the acceleration 0? This is easy. B to C. That's the intersection where they're at constant velocity. Okay, good. You guys are all good at this. Whoops. Where is the magnitude of this object's velocity increasing? A to B. It's speeding up. The magnitude of the velocity is increasing. Where is the magnitude of the object's velocity decreasing? C to D. Awesome. So basically, you all just showed me that you can do this. You can identify where acceleration is positive or negative. And you can identify where that is slowing down or speeding up. Remember how we said velocity had a direction? Well, it can be positive or negative. So if I say that this is, remember we talked about velocity or movement in one dimension being like being on a railroad track, going back and forth. If this is my origin point, if this is what I call 0, and my little car goes from 0 to 10 meters. Then, okay, this is my final position. This is my final x. This is my initial, whoops, my initial x. My change in x is my final minus my initial. So my change in x is 10.0 meters. Really, Moser, you had to point that out? Come on. We're fairly clever. I don't need to write this down. This is stupid. What if, instead of going from 0 to 10, my little car goes from 0 to negative 10. Well, my delta x is equal to my final position minus my initial position. My delta x is equal to negative 10 meters minus 0. What's my change in position? Negative 10 meters. So my displacement can be negative because displacement is all about the change in position from the start. We can have a negative displacement. If we're calling a particular point our origin, that negative sign can serve as a proxy for direction. Remember, we said velocities have to have a direction. The example I always used to use, because Route 7 is such a nice example, we imagine a perfectly straight Route 7 from the old high school straight to Rogers and straight to the river. Doesn't work that way, but okay. Where Beaver Local is origin. And we call north positive. If you head south on Route 7, is your velocity positive or negative? It's negative. If you're, because, so let's sort of prove this mathematically. Velocity is equal to delta x divided by delta t. Let's get rid of these guys. So, if my delta x is negative 10.0 meters, if it took me 5 seconds to do that, my velocity is negative 2 meters per second. Now, does that mean that I'm not moving or that I'm somehow moving? It means I'm moving in a negative direction. It means I'm moving in a negative direction. What does this mean for acceleration? So, let's say we have a velocity time graph. Okay, so as long as we're above that x-axis, this is easy. So where's the acceleration positive? Let's look at these individual sections. From A to B, is the acceleration positive? Yes, the slope of the line is positive. From C to D, is the slope of that line positive or negative? It's negative. So we have negative acceleration. So here, acceleration is positive. Here, acceleration is negative. Now, in section A to B, is that object speeding up or slowing down? Speeding up. The way to think about this, velocity is your y-axis. The magnitude of the velocity is increasing. Okay? 0 is your origin. At origin, you have 0 velocity. You are stopped. From C to D, you said acceleration is negative. Is the object speeding up or slowing down? Slowing down. This is easy. We like it. We're getting closer to origin. We're getting closer to 0 velocity. The magnitude of the velocity is decreasing. Now, from D to F, is the slope of the line positive or negative? It's negative. So is the acceleration positive or negative? It's negative. The slope of the line is negative. For this section, acceleration is negative. Now, is that object speeding up or slowing down? it is speeding up. Yeah, this is the part nobody likes. Because the magnitude of the velocity is increasing. You're getting further away from origin on that velocity axis. So you're speeding up, though you have negative acceleration. Yeah, I know, it's terrible. For section G through H, is the slope of the line positive or negative? It's positive. Positive acceleration. Object speeding up or slowing down? Slowing down. Because the velocity measurement is getting closer to origin. You're approaching zero velocity. So here's the sort of algebraic explanation. I'm fond of these. A negative times a negative equals a positive. Here you have negative acceleration in a negative quadrant. It's speeding up. A positive times a negative is a negative. Here you have positive acceleration in a negative quadrant. It's slowing down. Okay, we'll pick up tomorrow. Hey, have a good day.